So this is work that I did together with my colleague, Geir at the University of Illinois, and then the student we co-advised, Hussein Darir. Hussein just graduated, and he's now working at Ford Motor Company. This work has to do with the Tor network. And if you're not familiar with the Tor network, it's a way to hide the relationships between users who want to connect to, say, websites and the websites that they access. And the way that Tor hides this relationship is by sending traffic through a circuitous route that goes through a number of Tor relays, such that at no point can an observer tell the entire path and link the two ends together. There are many design challenges in the Tor network. One of them is balancing the load across all of these network of relays. There's about 6,000 of them at present, and it's been about the right number for a while. They're run by various volunteers. Some of them have access to very well-provisioned servers that are connected in data centers to high-speed networks, while others are just random computers that people have lying around that might have a very small, slow connection, and they have many fewer resources. And so in distributing this load, one of the things that we need to make sure is that the capacity of the varying capacity of the relays is taken into account. Now, to do that, we need to first be able to understand what the capacity is. And the way that this is done is by way of measurements. And the measurement for capacity is done by having something that's called a bandwidth authority send probe downloads through a content distribution network and measuring just how fast this download is. And this is used to try to figure out the capacity, the bandwidth capacity of the node. And this measurement, you can't use this measurement directly to estimate the capacity. Why not? Because while you're performing this download, there might be lots of other users who are using this relay at the same time for their downloads. And so this cross traffic, which is proportional to the current estimated capacity of the node, which is also something called the weight of the node that's assigned to the node, needs to be taken into account. And so this ends up being an estimation problem that you need to try to figure out. Now, I want to talk about two previous approaches to capacity estimation. The first one is something called SBWS, which is deployed in Tor, and it's an evolution of a few different estimation approaches that's been deployed since about 2019. And it uses these measurements in combination with bandwidth that's self-reported by the relay itself. So there's measurements that are done by the network, and there's measurements that are done by the relay. It combines them, and we've been working for the last 3 years, but it's really noisy. The estimates of a capacity of a relay, you can have the same relay, and its estimates will change over time because there's an error in the estimate. It's also potentially susceptible to manipulation because the self-reported value, an attacker can manipulate that and lie about their reported capacity. Most importantly, it's been engineered over the years to try to have good performance, but how well it works and why it works wasn't really well understood. So in previous work that we published in PETS last year, what we did is we tried to say, let's try to model what's going on here. And we came up with a really simple model of how capacity estimation works. And then we built a maximum likelihood estimator based on this model. And this model relies only on measurements. We do not use the self-reported data. And we were able to prove some convergence results. So I'm going to quickly recap that model for you and then talk about what we're doing in the present work. So the idea is that what we have is the really simple model is that we say, okay, there's a number of flows that go through a relay. There's our one measurement flow, and then there's a bunch of cross-traffic flows that happen that belong to other users. So we'll call the cross-traffic, we'll represent that by a random variable, which we'll call x sub t. The t is a subscript representing the time to be able to evolve this over time. And then we will make the simplifying assumptions that the capacity of the relay, the true capacity, is divided equally across all these flows. And therefore, the measurement observation is just the capacity divided by the sum of the one flow and this random variable. Further, this random variable, we'll model it as following just a Poisson distribution that's proportional to the total rate on the network scaled by the weight that's assigned to this particular relay. And so this simple model admits a fairly straightforward maximum likelihood estimate. If we take a single measurement and the current weight, we can derive this formula for a maximum likelihood estimation. But the other thing that we can do is we can apply a series of observations. We could look at an entire history of observations and try to compute a maximum likelihood estimate conditioned on all of these observations. Now, this is a problem that I asked my grad students, who are very good at math, much better than me, to figure out. And they went away for a number of weeks. They came back with this long, detailed write-up that had phrases like steering and approximation, Lambert W function, and lots of scary equations that we safely hid away in the appendix of our paper. And they came up with this formula. So this is a closed form formula that's an approximation to the maximum likelihood estimate. As best as we can tell, there is no closed form formula that's an exact representation of this. And so we used this formula to do a bunch of results. We were able to prove things about it. We were able to do some simulations about it, show good performance, and so forth. So we wrote that up in the PETS paper. But then we came across this new concept called probabilistic programming. What is probabilistic programming? Well, the idea is that you can define a program that represents a model, a probabilistic model, that ties together latent or hidden or unknown variables and observations. And so basically you say, here's some unknown variables that come from unknown distributions. My program is going to sample from that distribution, do some computation, and say, this is what the observations should come out. That's what I code up. Now, the programming framework then uses machine learning-based optimizers to infer the latent variables based on observations. So you code up the forward path, essentially, and it does the backwards inference. What does this model look like? Well, this is a slightly simplified implementation of a model that essentially captures this equation, this mt equals c over xt plus 1. The first line defines the capacity, c, as being sampled from an unknown distribution. The second line represents this random variable that represents cross traffic, xt in our model, that's coming from the Poisson distribution. Then we apply a distributional transform that I hid away the details here, but it uses this sampled value, c, capacity, and transforms the Poisson distribution from xt to c over xt plus 1. And then this transform distribution is then used to sample a new value. And then this last line says this sample corresponds to the measurement that is passed in as an argument for this model. And then with a few extra lines of code, we can now say, okay, given this measurement and then all other parameters, the weights, the number of passes, and so forth, infer what the distribution, what the value of C is. The important part is that it's very straightforward to go from this model, which captures a single observation, to iterating over a large number of observations. And so doing this step, going from this simple maximum likelihood estimator to this really complicated approximation, is really simple in NumPy or in general probabilistic programming. You just had to add essentially these two lines here and change the weights and measurements from a scalar to an array. So this is something that we were able to do relatively simply. And then we said, okay, let's plug this in on the same data that we used for the previous paper. And the thing that you can see here is that the probabilistic programming represented in red here is giving us as good or maybe even just slightly better, more accurate estimates of capacity than our closed form approximation is. with a lot less work. Now, that was step one, is that we say we can use probabilistic programming in this context. But the real power comes from the fact that now that we have this program, we can amend it to remove some of the simplifying assumptions that we made in our model. So one of the things is, if you look at the last slide, there's actually 4 classes of relays that Tor has. Our model in the PETS paper didn't capture this at all. And so as a result, it worked well for some classes and not so well for others. So we changed our model to capture these classes. And then we also wanted to look at the fact that this assumption that the capacity of the relay is divided equally among all flows. We wanted to refine that to capture some important interactions. And so let me talk very briefly about this. You can find more details in the paper or in the extended dance remix of this talk that will be posted after the conference. So what we're looking at is the fact that there are bottlenecks that happen at various points in the path. So if you look at the relay that this path goes through on the right, it's probably not going to be the bottleneck of this flow. And so this flow isn't going to utilize all of the capacity that's available at this relay. We have in our simulation complex code that implements this. And the problem is that this code can't be directly plugged into the probabilistic programming. I mean, it can, but the problem is that this just doesn't scale. The inference algorithm will never terminate because this requires you to instantiate every single path in the network, hundreds of thousands or even millions of them. Instead, what we do is we're able to try to infer the bottleneck capacity of each relay by using the measurement flow, as saying the measurement flow must be bottlenecked only at the relay, and therefore that is the bottleneck capacity. And based on that, we can separate the relays into classes based on whether they have a faster or slower bottleneck capacity than our relay, and we can then treat each class separately. Again, I'm going to skip over the details. I'm just going to quickly throw up some results based on our evaluation. We did evaluation of the entire network using a liquid flow model simulator where we just model the capacity or the bandwidth allocated to each flow. And then we had a really high fidelity simulation that runs the actual Tor code using a tool called Shadow and over a simulated network. And here we have to use a scaled down network because we can't run 6,000 copies of Tor and get results within a reasonable amount of time. The results here from the high fidelity simulation, but you'll find the low fidelity results are similar in the paper. And the two kind of quick takeaway things that I wanted to show you is that, first of all, the estimation error is much smaller and is now low across all classes of relays in our new and improved model. And this makes a difference for performance. This makes a slight difference if you at the median of the performance, but in this graph, the lines of different colors essentially show the interquartile range of the bandwidth that you will get for the flows that for each different method. And so the red one, which is our new method, has a much narrower performance band and much faster convergence, so it reacts to changes much faster. So to conclude, one of the most interesting things to me has been discovering this probabilistic programming approach and showing that in lots of applications where we need to do probabilistic estimation, this allows us to save manual labor and model much more complex systems than we would if we're doing things manually, with the caveat that we need to be mindful of the performance and scalability. And then in this specific case, we're able to show that using this in the Tor context very significantly improves performance, in particular, makes performance much more predictable rather than having a lot of variance. And at this point, I'm going to stop and take a couple questions.
I have a question about if your approach deals with this issue that we've seen in Tor, where people who run multiple relays on the same machine, when you do the measurement of any one of those, it tends to estimate because it's giving you the spare resources on the machine. And then you measure the other one and they say I have this much extra capacity. And then you sort of get into this weird situation.
So no, this is not something that we're almost certainly not captured definitely not captured in the model or the shadow simulation.
Yeah.
I mean, I could imagine amending the model to include this if you know that two systems are co-located, but I don't know if that's the right approach here.
We need a new flag in Tor to do that, but
yeah.
Okay, I just wanted to see if the model...
Yeah, that's really interesting. I would be interested in talking more about this.
Thanks.
Hi. So on a relay at any given point of time, there's a bulk traffic and there's a bursty traffic that is going. So in your model, do you incorporate these two and you try to differentiate them?
No. So essentially, our model basically takes a baseline level of traffic that imposes some load on the network. And so you can kind of think of the interactive traffic, the non-bursty traffic, as saying, okay, it happens at a lower is similar to bulk traffic, but at a lower frequency. So you can, maybe trade this off. So our model doesn't capture that because our model just says the traffic gets divided among flows. I think our intuition is that this approximation is good enough. There's a question as to whether it would be possible to refine the model to capture bursty traffic. But that would be something that we'd need to look at in the future.
Thank you.
Thanks for the question.
Great talk. Have you considered taking a factor around locality? For example, if you have a circuit that's set up that has 3 German nodes versus a node in the US, a node in Germany, and a node in Australia, that's going to have potentially some factor in essentially if you have localization that you may be able to get, even though there's less bandwidth there, it may still be faster because they're all geographically closer.
Right. So that's a factor that can be used in selecting paths. There's, essentially, in terms of load balancing, you can think about there being two components. One is a capacity estimation, and second is this path selection based on these capacity. We haven't done work that does this kind of path optimization, but there's been other papers that try to say, you can do some locality and looking at some trade-offs. So for example, if you pick nodes that are too close together, then you might be able to give away something about your position. There's a number of papers, I can send you a couple of references that explore that facet of it. But underneath it all, you still need to have a good capacity estimation to not overload any of these nodes. So I see that as almost orthogonal.
Yeah, let's thank the author again. Yeah, thank you for the nice talk.